So I want to start today with a sketch of how you might program the searching pi algorithm. Then we'll break, and Danielle will do her thing. Danielle, are you around here somewhere?
She's in the bathroom.
Okay. And then we'll finish off with some more exercises or examples of reading and playing with files. Let's see. Let me pull up the assignment here and just remind everybody how it's supposed to work. And in fact, maybe I'll run my demo program again just to get it in everybody's head. So you'll recall that the program is going to search for a sequence or a string of digits inside this, inside the first million digits of pi. For example, our zip code starts at position 7171. If you look at the digits of pi, let's go here, and think about the task of finding a particular string, a particular sequence of numbers, you can imagine how this is going to have to go. You've got the thing in your hand, the string of numbers, which we'll call the key. The key, let's say it's 265. 265 right there. So think about, just visualize in your head how this is going to work. You start off with 265, and you look at the 2. Right? You're not going to have a match. You don't have a hope of a match unless the 2 matches, right? So you start sliding along until you get to, I should have picked a different number, 2. And when I get that match, then I check the second character in the string, and if that matches, I check the third character in the string, and if that matches, I'm done. If I get a match on the first character, let's do something a little more interesting. Let's do 932. So 932 is right here. So you start sliding across until you find a 9. And then the 2 doesn't match the 3, so you pick up and you try to match the first character of the key to the 2, which doesn't go. And you keep going, and you get down here, and the 9 matches, but the 7 doesn't. So you stop, and then you slide over, and 9 doesn't match 7, but it does match 9, and then it matches 3, and it matches 2, and you're done. So you can imagine what you can imagine is this little string of numbers is sliding along, and whenever it encounters an initial match, it tries to grow out to a full match. And if it fails, it moves to the next character. Now, there are more sophisticated ways that we can do this, but I'm not interested in that at this point. I'm just interested in the very simple, when the first digits match, try to match more. And if they don't, move to the next digit. You can be a little more sophisticated, right? If the first digit matches and then you check the second digit and that doesn't match the first digit, you might as well skip to the third digit kind of thing, right? You can be more sophisticated, but to be honest, it doesn't really save you a significant amount of time, and so it's not really it's worth thinking about as an academic exercise, but in terms of raw computation, it doesn't really save you that much effort. That's called looking ahead. All right, let's think about how we should organize this program. Okay, let's sketch searching pi. If you look at how I run this thing, All right, there's a prompt for a string of numbers. I type in a string of numbers. I hit enter. It searches, and then it prompts me again for a string of numbers. Okay. Oops, that's not good. All right. That's how it works. How do you? Let's sort of hash out a sketch. Two sort of major components of this program. What are they? Okay. Even bigger than that, but that's part of it. Sorry?
Loading.
I would say sort of the interface, how you use the program, and the searching for the data are the two big components. And that's the prompt, the response, etc. And then there's the actual search. Ami?
Do you have to specify that there's a million digits, or is it like?
Actually, no. Last time we're going to take advantage of a feature of strings, in essence, to let us know when to stop. But let's so the interface here is a prompt and a response. What happens between the prompt and the response? The search. Yeah, the search. Okay? So you prompt, you do the search, you report the result. And that just happens over and over and over again. All right. I think that you guys have the tools to deal with that aspect, right? Your cout, your cin, and so forth. I want to focus on search. And I encourage you to make search a function. And what information does the search function need in order to do its job?
Data file.
So it needs the digits of pi and what other information?
What digit are you searching for?
The string of digits. So this needs the digits of pi, and it needs the key. It's the string of digits. Given that information, it goes through some magical process, which we'll talk about in a minute. What is this function expected to provide you?
Position of the string in the digits.
Right, the first occurrence of the string in this larger collection of digits. So how should it communicate that information back to the calling program? Unsigned int as a return value, perhaps? Okay, so it should return an integer. And it can be unsigned if we really care about overflows. Is a signed integer enough for the first million digits of pi? Yeah. The largest that a signed integer can be is approximately what? Approximately 2 billion. And that's more than enough capacity to return a number between what and what? 0 and a million, yeah. What is 0?
Well, I guess 1 in a million.
So 1 in a million. I actually like 0, though, Andrew. 0 is useful. 0 is a nice way to tell the user or to return the fact that the string was not found. Right? So yeah, I actually like 0 to a million. So this is going to return an integer, and it's going to be a range. It's going to return 1 to a million for the found position, or it's going to return 0 for not found. And I may have, I don't remember what I did in my assignment. I remember talking about this, but I don't remember. I think I had fail equal -1. You can make fail 0. Okay. -1 is a common value for fail. So, all right. So the advantage of using 0 for not found is if we ever do decide that we want to search using unsigned ints, we can still use 0 as the flag for not found. So either one is fine. This is a way of signaling using the same data type. It's a way of signaling failure. Okay. How should we get the information into the function? In particular, I guess what I'm asking is, what are the arguments to the search function? Okay, representing what?
The key.
Okay, so a string for the key. Now I said this thing needs 2 pieces of information. You kind of have a choice here. You can open the file inside the function and search, or you can open the file in the calling program and pass the information into the function. It's up to you. What do you want to do? You want to open it in the main? There are actually good reasons for doing that, and I'll talk about that a little bit later in the hour, perhaps, or certainly on Friday. So I would suggest that you pass the digits of pi into the function as an argument as well. What data type should be holding that argument? Should be holding the digits of pi. What kind of data type? Actually, yeah. So we can have a string, which we can call digits or something similar. How should these guys be passed? By value, by reference, constant, not constant? They're both, neither one of these would be expected to change inside the search function, right? Searching for a particular key does not change the key. Searching the digits of pi for a particular key does not change the digits of pi. So certainly constant. You also mentioned reference, Carter. Why? Be more specific. How does that help? It's not going to make a copy of the million digits of pi, which is not desirable. Especially if you want to scale this thing up to more digits, like 1 billion digits of pi. Right? 1 billion digits of pi. Each digit is a character, right? Each digit is a character, and a character takes up how much memory? Do you remember? 1 byte. So 1 billion digits of pi is approximately, it's actually a gigabyte. So 1 billion digits. How about 1 million? That's approximately a megabyte. You know, in modern computing, a megabyte isn't a whole lot, but these are still things you should be thinking about. There's no reason to pass this thing by value. There's just something on the face of it wasteful about passing this thing by value. So yes, constant reference and constant reference. Oops. So the prototype or the declaration of this function would look a lot like this. oops, const string ampersand const string ampersand. These are decisions that you have to make whenever you sit down and write a new program. How do you want to organize the program? What are the functions that you're going to write? What are the arguments and types? What are the return values? That's actually the easy part. Well, maybe not. In some cases, that can be quite hard. Definition. By definition, I'm talking about now what happens inside this function. So you're inside the function. You have two pieces of information that have been provided initially, the key and the digits. And they are represented by strings. The first digit, for example, let me just remind you. So the first digit in the key is key 0, right? Remember that? So I can do character-wise access of a string by using this array subscript notation or this array index notation. What's the last character in the key? Remember how to do that? Yeah, and the specific syntax is key size -1. So we've done now some object-oriented programming, and we see now that dot size, or we should now have a pretty good idea of what dot size does. Right? Size is a member function of the string class, and it returns the number of characters in the calling object. What's the calling object in this usage? Key. This is a string object, and it's calling the size member function using the dot operator. So the calling object is key, and the dot size member function tells you how many characters are in there. Constantly have to remember that the number of characters is different from the biggest index in the array. If the number of characters is n, then the array indices go from 0 to n-1. We can do the same thing with digits. The first digit of pi is, let's call it digits, is digits 0, and the last digit is digits size -1. So I don't remember, was it Ami or somebody who had the question about how do we know how many characters there are, and do we have to sort of put 1,000,000 into our program or 1,000,000,000 or whatever? Thankfully, no. The string is going to keep track of how many characters are in the key and how many characters are in the digits of pi. So this program written properly will let you easily switch between, say, 1,000,000 digits of pi, 10,000,000 digits of pi, 100,000,000 digits of pi. And in fact, I've provided those links to those files on the web page if you're interested in doing more in-depth searches. I will warn you that this guy, this is nearly 100 megabytes. There are better ways to store the digits of pi than as characters, but that's the way I'm giving them to you at this point. All right, we've got the data inside the function as strings, leaving aside the problem of how we actually get the data into those string variables. We now have them in the strings. Think back to how I opened the class with these little thought experiments, little 3-digit windows of integers that I slide across and I look for a match. How do you think the inside of this thing is going to look? Sure. You should have a for loop. And that for loop, at the very least, you're going to have to compare the first character of the key to every digit in pi, right? Does everybody see that? No matter what else happens, I've got to compare the first digit of the key to every digit in pi. That suggests a for loop that should do what? It should go all the way across the digits of pi, right? So for I equals 0, I less than digits size, I plus plus, that's going to do something for every digit of pi. Inside this for loop, now this for loop is going to start by comparing the first digit of the key to the current digit of pi. So you're always going to be looking at key 0, and you're always going to be comparing it to digits I, right? Okay, so how do you see this continuing?
Compare key 0 to digit I, and then that's equal and break down the forward. But we made that index though, right? So it's really wrong.
So you're going to look at that comparison? Okay. And if that's true, what are you going to do? Then I'm going to try to continue. So if this is true, then try to continue the comparison. If it's false, next loop. So go to the next I. Okay, let's talk about the true part. I will say that this first time through, what I'm doing is sort of following the intuitive approach. Once we sketch out this intuitive approach, what you're going to find is you'll be able to write this in a way where you don't really privilege that first comparison. But I'll let you think about that. So, if it's true, you continue the comparison. If it's false, you go to the next I. Let's talk about continuing the comparison. Now, to continue the comparison, it's a little bit problematic, right? We don't really know how long the key is. So this is going to rely on what? Yeah, this is somehow going to depend or going to require a loop that runs on the order of key.size times. So we need a loop We need a loop that continues through the remainder of the characters in the key. And this loop, let's say the loop index is j. What comparisons, what's the formula? What characters are being compared? Give me the indices of those characters. That's exactly what it would be. I is the starting character position, right? Once I get to a matching I, now I try to grow past I using j. If any one of these guys fails, I'm done. Go to the next I. Right? So if these are all true, then I plus or minus 1 is the match position. If any of them are false, then you break out of the loop and move to the next I. Make sense? There are a couple of things that you have to be careful about. What if I'm very near the end of the digits of pi? I'm out near 999,997. And what if my key is 5 characters long? What's going to happen if I'm not careful? It won't loop around. It'll give you a segmentation fault. It'll run off the end of the string and give you a segmentation fault. So you need to add a little check in here. We know that I is always going to be in range. But what we don't know is I plus j. Is I plus j going to be in range? If I plus j goes out of range, you're done. You've got 3 digits of pi left at the end, and you're trying to match a 5-digit string. You're done. That's not a match. It might be a match if you had more digits, but we're going to call that not a match. Okay, I'll let you think about that, hack away at it a little bit, and then we'll talk more about it on Friday after you've had a chance to think about it, Carter.
Can you put the check up at the top and subtract the key size from digit size?
There are an infinite number of different ways of doing this. So whatever works for you is fine with me. And I look forward to seeing how different people attack this problem. This is just one way of dealing of coding this particular, and I haven't really even fully coded it for you. I don't want to give everything away. Danielle, yes, let's do yours, and then we'll do some more interesting stuff playing around with files. Danielle, do you need to log in?
I just need to get to my email.
Your email. Let's go here. Well, let's just try this. Is it webmail email? I don't know what it is. I'm gonna. Kuba had issues with this before, so I'm gonna.
Usually just go to the webmail
there.
website.
Go ahead.
Okay. Was it unhappy? Oh, it's fine. Okay. Oops.
Is that what it is? Would I have webmail or something? Yeah.
Okay.
The way I read my mail is so far removed from that
Okay, let's do this.
I want.
If you ever want to read a really good biography,
How do I do?
Alan Turing's biography is really interesting.
Okay, I guess that's fine. Okay. So I'm going to be presenting on the Turing test. So the Turing test was sort of developed by Alan Turing in his 1950s paper, Computing Machinery and Intelligence. And he was looking at the idea of artificial intelligence, and he sort of wanted to look at it in a way that was more testable. And so he replaced the question of can machines think with can machines do what we as humans can do? So the Turing test is a test to determine whether something is a machine or a human. And sort of the original Turing test type thing was the imitation game, which was a party game in which a man and a woman left the room, and guests made a list of questions and gave them to the man and the woman, and they sent back typewritten responses. And the guests had to determine whether it was the man or the woman that responded, and the man and the woman were trying to trick the guests. So the Turing test equivalent of that is a computer that's trying to trick the judge into believing that it's a person, or either that or a judge trying to determine whether it's talking to a computer or a person. So two of the first programs that sort of passed the Turing test were ELIZA and Perry. So ELIZA was developed in 1966, and it had a personality of knowing nothing. So a user would talk to ELIZA, and based on its questions, ELIZA would analyze for keywords and would respond either with the keyword or with a generic response or a previous comment. And Perry, on the other hand, was sort of ELIZA with attitude. Perry's personality was a paranoid schizophrenic. So a bunch of psychoanalysts would pose questions to Perry and would talk to both Perry and to actual schizophrenic patients and try to determine whether it was talking to the program or talking to a real person. And psychoanalysts only guessed correctly about 50% of the time, which is consistent with random guessing. So some variations of the Turing test are the Feigenbaum, is that how you say that? Test, which compares the abilities of machines against the abilities of experts in specific fields. So the first program that kind of tried to do that was IBM's Watson, which won Jeopardy. And so Watson had a bunch of different sources, including a full text of Wikipedia, but didn't have any internet access. So the idea of could it search through and try to find the answers before a real person could. Some modern day programs that do Turing test things are chatterbots. And an example of that is CyberLover, which is a malware program that you encounter online. And it's a program that tries to flirt with you to get personal information or direct you to a website where you can contract a virus. So yeah, there are lots of XKCDs about Turing test type things. So sort of a reverse Turing test is a CAPTCHA, which is a computer trying to determine whether it's communicating with another computer or a real person. And the idea is that these characters are so warped that only a person would be able to determine what it actually said. But there's some things being developed as workarounds like optical character recognition, which would allow computers to determine what was actually being put there. Some criticisms of the Turing test are, although it was developed to look at artificial intelligence, it actually is looking at how well computers can mimic human behavior. So programs that can pass the Turing test really well do things like add in typos. If you insult it, it gets really angry. There are delays in responses. So it's sort of introducing this idea of artificial stupidity. It's making the computer more stupid than it actually is. And programs that actually do show artificial intelligence don't necessarily have to pass the Turing test, so whether the Turing test is really useful at all. Any questions? Okie dokie.
Nice job, Danielle. She hit all the high points.
I'll get you. can get out of this, that is. Okay, so there's that and that. Okay. So hack away at searching pi a little bit between now and Friday, and then we'll come back and we'll talk about any questions that you might have. I do want to, well, I'll talk about it in a second. Let's go look at a couple of examples that I've already constructed here. So a few of you in here have, I think a few of you in here have seen me use the word cat to show what's in a file. Yes, no, maybe some of you. So cat is just a simple Linux program that will take the contents of a file and just dump it to the screen so you can see what's inside of it. And it's just, you know, it's sort of one step short of opening it up with VI. I mean, you could always open it up with VI, but maybe you don't want to run VI and get into all that mess. You just want to see what's in the file. So there's this thing called cat. And you just type cat and it prints the stuff to the screen. We actually now have the ability to write a cat function, and that's what I want to talk about right now. And I've already pre-written this thing, and I want to talk a little bit about last time we saw how we could open a file if we already knew its file name. But that's a severe limitation. What we'd like to be able to do is open a file that is whose file name is supplied by the user. Because, after all, that's what you do when, for example, you VI a file. Right? Vim doesn't know what file you want to open. How do you communicate to Vim what file you're going to open? You type it on the command line, right? And then there's some mechanism that at the moment is opaque to us, whereby the string words.cpp gets passed into Vim. Then Vim actually attaches that file to a file handle, and forever after in the Vim program, all of your editing is done through the file handle, not through the file name. That's actually the whole reason that we use file handles, so that a programmer can write a program that uses an external file without having to know the name of that file. So the file handle is a proxy for the file name inside the program, and it gives the programmer something to write with. So let me go back into my cat program. And you see something new here. All the time before when we've written our programs, we've always just had empty parentheses here. But now I'm giving main 2 arguments. The first argument is an integer type, and it's argc, which stands for argument count. And the second one is, it's a little fancy, and I'm not going to get into what the star means, but the second one is an array of strings. So what this would be, for example, in argv0, the 0 entry of the argument array, would be the name of the program as it was typed on the command line. So in this case, it would be a.out. And then argv1 would be the first argument after separated by space. Argv2 would be the second argument. Argv3 would be the third argument. And that's a way of getting that information into the computer. And the first thing that I have when I'm doing this is I check to see if the argument count is less than 2. The way that I want to use my program, I want to dump the contents of a file to the screen. So it's going to require it's going to require at least 2 arguments. It's going to require the name of the file, cat, and the name of the file name. So if I try to run this program, without any arguments, it sees that the argument count was 1. And it says, you're not using this thing correctly. Here's a usage statement, cat file name. So then I go back and I do a.out Now the argument count is 2, and it gets past that check and opens the file and dumps it to the screen. So that's this little guy. If I get past this guy, then I know that sitting in argv1 is the name of the file. So what I'm going to do is attach that file to an ifstream object called input. It can be any name that you want. Any C++ legal variable name is okay there. I choose to call it input. I also tend to capitalize my file handles. It's just a stylistic thing that I do to help me identify, oh, that's a file handle. And the next thing I do is I check to see if it was opened successfully, because it's entirely possible that I would misspell the name of the file. So, for example, maybe I would do something like cat.cp. Failing to find that file, failing to find a file named cat.cp, it quit. This is fairly typical when you're accepting file names from the user. You check to see that they're using the program correctly. You try to open the file. If you can't open the file, then you print an error message and exit. And in both of these cases, we have the exit 0 command, which immediately terminates the program right at that point. And if you want to use exit 0, we've talked about this before, it's in C Standard Lib. So we've now, at this point in the program, successfully opened the file that we would like to dump to the screen. What I'm going to do now is just go through the file character by character. We talked about get last time. Get goes out to the input file stream and grabs the next character, whether it's visible or invisible, and it stores it in the character variable C, which I've declared up at the top. Every time I go out and I ask the file for some data, I should check to see if I've gone past the end of the file. If I have, I should stop. So whenever you go to a file, you should check to see if you've gone EOF. If you've gone EOF, you're done. You've gotten all the data out of the file that you can. And break. Otherwise, print the character to the screen. And close the file. That's it. This will dump all of the characters in the file to the screen. Let me show you how that works. So a.out, cat.cpp. A lot happens in a very short period of time, but it went through the file character by character and dumped it to the screen. Okay, this is kind of interesting. We can start to do more interesting things than just catting. Let's move to the next file. Let's look at words.cpp. Okay, words.cpp has the same initial gobbledygook. This is always the same. You can call these things anything. You can call argc Fred, and you can call the argument array Ginger or whatever. But these are traditional names, argc and argv, and you see them in programming literature all the time. And these are your only options. Either these parentheses are empty, or they have 2 arguments and they look like that. That's it. That's all you can do with main. So if you want to use this method, you can literally just copy this stuff out of this example program that's on the web page and use it. What I want to do is go through this file in a slightly different way. So at this point, I have successfully opened the file, and instead of reading characters, I'm going to do this. What's going on here?
You're reading words.
Yeah, I'm using a string data type, and I'm doing a formatted read from the file. So this is going to ignore what? It's going to ignore invisible characters, spaces, end lines, etc. Let me print out what this looks like. So I went to the web and I grabbed the opening paragraphs of 4 important pieces of literature. Camus' Stranger, Kennedy's Confederacy of Dunces, the King James Bible, and Melville's Moby Dick. Let's run this thing on any one of these files. So I've recompiled this thing. Let's run it on Camus. You see some of the stuff has made it into the string variables, and all the invisible stuff has been stripped out. Let me print it out in a slightly more visible way. Words. Let me put an end line in there. So if I put an end line in there, then you begin to see what's different. I'm kind of getting words anyway. Most of the time it's okay. It's kind of fooled by various pieces of punctuation. But generally speaking, that looks like it's chopped the thing up into words. And then what I did was every time I successfully got a new string from the file, I just counted it. So there are 32 words in the opening paragraph of The Stranger. I could do this on the next one. And there are 161 words. I'll use the word loosely. 161 words in the opening paragraph of Confederacy of Dunces. And I can go on. The King James Bible, 39 words in the first paragraph of the King James. And what was the last one? Melville. And 204 words in Melville. Okay, let's go back into words here. I'm going to get rid of the cout statement so we can just look at the word count. So we go ahead and grab the words. We set the word counter to 0. Every time we successfully get a word, we increment it, and when we're done, we say there are this many words in the file that I specified. Oh, good Lord. I'm not sure what that actually says about these authors or these works, but here's a systematic way of analyzing these texts. It turns out that this approach to analyzing texts has seen a renaissance in recent years with the advent of computing and the advent of full text access to these works. If you have the full text of Moby Dick, and you have some primitive C++ programming skills, you can actually do some really interesting textual analysis on this. Beyond what maybe the English professor was doing 20 or 30 years ago, which was sort of analyzing the prose and looking at symbolism and metaphor and all that sort of stuff. Now, this in say the last 20 or so years, they've done more sort of statistical analyses of these texts, and I put a paper on the web page here. Actually linked it on Monday, but finally getting to it today. Here's an example of the kind of literature that's being generated using this kind of textual analysis. So Frank Baum wrote The Wizard of Oz. And you may or may not know that The Wizard of Oz is just one of many novels in a series set in the same world as The Wizard of Oz. But sometime towards the end of his life, he started collaborating with a ghostwriter, and he died And the ghostwriter, I forget her name off the top of my head. Maybe it's... Anyway, the ghostwriter took over the series and continued it for the publisher for probably another 5 or 6 books. And the publisher was pretty mysterious about when Baum's work stopped and when this other woman's work started, because it was continually published under Baum's name. This guy was able to conclusively show that when the authorship changed. And if you look through this, you get kind of a hint of how the author was able to do this. He gets into what's called stylometry, which is looking at certain kinds of words and the frequency of use. And every person has a unique stylometry associated with their writing. And he was able to definitively show that it was at this point in the series that Baum stopped and this ghostwriter started. Similar analyses, have people heard of the Federalist Papers, were written around the time of the Revolution? They're a quagmire, right? They were written by Jefferson and Madison and there's one other that is John Jay. Thank you. Yes, same last name, right? There you go. So it's funny because these are founding documents for the United States, and really important documents. And as time passed, Jefferson and Madison and Jay all laid claim to the same pieces of work, right? When one piece of work was really well regarded, they were all claiming to have written it, even though they wrote it anonymously. Why did they write it anonymously? So they wouldn't be killed? Yeah? So but once the country was established and it was okay to walk around and say, yeah, I wrote that, they all started laying claim to these Federalist Papers. It's now been pretty well resolved based on, you take Jefferson's stylometry, you take Madison's stylometry, Jay's stylometry, and it's actually now quite well known which one was which. And it turns out that some of the papers were co-authored, and back and forth, so it's complicated. But it's an interesting area of history and humanities that flows from this kind of analysis. We'll talk more on Friday.